You know the feeling, right? You're in the middle of a project, or maybe deep into a game, and suddenly the laptop on your lap feels more like a skillet. Well, that heat, it's a physical clue to this incredible battle happening trillions of times a second inside its microchips. So let's dive into that. We're going to see how engineers are using what's basically a virtual crystal ball to manage that heat and design the future of tech.
Yeah, it's a feeling we all know. You're pushing your phone or your laptop to its absolute limit, and it pushes right back with a wave of heat. But what is actually going on inside to create that? It's not just a sign that your device is working hard. It's really a symptom of a huge engineering puzzle.
And here's the thing, that heat isn't just an inconvenience. For the engineers who design these tiny, powerful systems, heat is everything. I mean, if they don't plan for enough cooling, if they underdesign it, the whole thing can literally cook itself and fail. But if they over-design the cooling, the device gets bulky, expensive, and heavy. It's this incredibly delicate balancing act between power, cost, and the laws of physics.
So to even begin to tackle this problem, engineers start with a surprisingly simple and really elegant analogy. It turns out the way heat moves through a chip follows almost the exact same rules as electricity flowing through a circuit. And this is a fantastic way to picture it. Over on the left, you've got a basic electrical circuit, and it's driven by a voltage difference. On the right, a thermal circuit, driven by a temperature difference. If you understand one, you've got a massive head start on understanding the other. The power, which is the source of the heat, acts just like an electrical current, flowing from hot spots to cold spots. And what's really wild is just how deep this parallel goes. Think about it. Electrical voltage? That's just like temperature. The flow of current? Well, that's the flow of power, of heat. And electrical resistance, the thing that slows down current, has a direct twin in thermal resistance, which slows down the flow of heat. This amazing duality means engineers can basically use the same toolbox they use for circuit design to figure out a chip's thermal behavior. But right here is where our story takes a really fascinating turn. As our electronics have gotten just mind-bogglingly small, this nice, neat analogy, well, it starts to fall apart. See, down at the nanoscale, the electrons that carry all that current start playing by a totally new set of rules. Inside the transistors of a modern processor, and some of these are now literally smaller than a virus, the distances are so short that electrons just don't behave like they do in a normal wire. They can do something that sounds like it breaks the laws of physics. For just a fleeting moment, they can travel faster than their own speed limit. This is called velocity overshoot. Here's a way to think about it. Normally, an electron zipping through a silicon crystal is constantly bumping into the atomic lattice, and that limits its average speed. But what if the distance it has to travel is incredibly short? Well, then it can just blast across that gap before it has a chance to have enough collisions to slow it down to its normal top speed. And this quote right here, it nails the physics of it. That energy relaxation time is just a fancy way of saying how long it takes an electron to shed its extra energy through collisions and chill out. In today's chips, the transit time, how long it takes to get from A to B, is so short that the electron is already gone before it can relax. It's like a microscopic drag race, and for a pick a second, the electron actually wins. So if that simple electrical analogy breaks down, how on earth can engineers predict this chaotic, rule-breaking behavior? Well, they can't use a simple formula anymore. They need something way more powerful. They need to build a virtual world and just watch what happens. And that's the key. When the physics gets this weird, this complex, you have to throw out the simple rulebook and move on to sophisticated simulations. To really understand velocity overshoot, you have to model the journey of individual electrons as they literally ricochet through the crystal lattice. The tool for that job is called a Monte Carlo simulation, and yes, it's named after the casino, because the whole method is built on probability and randomness. What you're really doing is simulating billions of microscopic games of pinball all at the same time. The simulation follows one electron, lets it fly, and then uses random numbers to decide when and how it collides with an atom and which way it bounces off. So what does that look like in practice? It's basically a 4-step dance, repeated over and over. First, the electron gets pulled by the electric field and speeds up. Second, the simulation rolls the dice to see if it collides with something. Third, if it does, its new path and energy are calculated. And fourth, you do it all over again, millions and millions of times. By averaging out all of those random paths, a shockingly accurate picture of how the electrons really behave emerges, and that picture includes that elusive velocity overshoot.
Okay, so what's the big payoff for all this incredibly complex simulation? It lets scientists test drive the materials of the future before they're even really made. They can literally stage a virtual race between electrons and different types of semiconductors to see which one is going to perform best in the next generation of gadgets.
So, on our virtual track today, we've got two big contenders. In lane 1, gallium nitride, or GaN. You might have heard of it. It's already making waves in high-powered chargers. In lane 2, a newer challenger, indium nitride, or IN. Researchers think this one could be even faster. The race is on.
And here are the results. This graph is the direct output of all those Monte Carlo simulations. Each line is tracking the average speed of an electron in a different material right after a powerful electric field hits it. That bottom axis is time, measured in picoseconds, which are trillionths of a second. The vertical axis is speed. This is the race frozen in time for us to see.
So, what did we learn? Well, the star of the show is clearly indium nitride, the IN. Just look at that top line. It's not even close. Its electrons hit a much higher peak speed, and they hold on to it for longer. For performance, that is a huge deal. But also, look at how quickly that peak drops off. This incredible speed, it's a fleeting advantage. It lasts for maybe 2 picoseconds before collisions take over and the speed settles back down.
3 picoseconds. That's it. That's the entire window of opportunity. 3 trillionths of a second. It's an amount of time that's almost impossible to wrap your head around, but in that tiny sliver of existence, the physics of the future is being decided. Designing a transistor that can actually harness that fleeting burst of speed, well, that's the holy grail.
And that brings us all the way back to our hot laptop. By precisely simulating and understanding the split-second velocity overshoot, engineers can design chips that are way faster and more efficient. They can squeeze more performance out of less energy, and that ultimately means creating devices that are more powerful but run cooler.
So the next time your phone or your computer gets warm, you'll know. It's the echo of trillions of tiny electron races happening inside. It really makes you wonder, as we keep shrinking our tech down to the atomic scale, what other bizarre, counterintuitive quantum effects are just waiting for us to discover? It's just a reminder that the future is being built right on the very edge of what we understand.